Okay. Now the first part here is just a proof, a standard proof which comes up many times in the proof by induction. If you want to look at proof by induction, you can see the proof that way. But just for a change, I'll show you a different proof for it, which would have worked. It would have worked for the year, I think 1984. Let's have a Okay, sorry, I just got an email there. It would have worked in 1984. This method I'm about to show you, the Maclaurin series, because I think that was still on the exam. So cos theta plus I sine theta power n. Cos theta is 1 minus theta squared over 2 factorial plus theta 4 over 4 factorial, etc. And then that's plus I sine theta minus theta cubed over 3 factorial plus theta 5 over 5 factorial. So what you can do is bring that I inside. So I times theta is I theta, and then that's I times theta cubed. But what's I cubed? That's equal to minus I. So you can just put that inside as I theta cubed over 3 factorial. And likewise, you can do the same thing here. That would be I theta power 5 over 5 factorial, because I power 5 is I. So now these all can be written like this. And then you realize you can kind of do something similar here at the front. You can change the 1 into I power 0. You can change minus theta squared into plus I theta squared, because I squared is minus 1. And I power 4 is plus 1. And then the second one here. And if you look closely, and you could change I 0 into I theta 0, because that's a 1, and you can put that over 0 factorial. And likewise, you can change I theta into I theta 1 over 1 factorial, and you'll notice that you have all the terms of the exponential function. You have 0, you have 1, you have 2, you have 3, you have 4, you have 5. So this will equal E I theta. Now, this all has an n on it, so this has an n on it. So this would equal E theta n I. So then by just going backwards here, except you can replace the theta with theta n. So you can get cos n theta plus I sine n theta. Now, like I said, this proof would have worked in 1984, but you may not have seen Maclaurin series before, so you can use the proof by induction technique here as well. But I just wanted to do something a little bit different, since the proof by induction comes up a few times. Okay, the second part is just to deduce this. Well, I mean, that's pretty obvious, because the n just comes down from... Oh, yeah. You can't use De Morpham's theorem with the plus here. So what you're going to have to do is temporarily change it into cos minus theta plus I sine minus theta power n. Then you can put the n in, minus theta n plus I sine minus theta n, and then you can change it back into cos theta n minus I sine theta n. So you can do this because cos is even and sine is odd. That's why you're allowed to make the sign change like that. Theta can change to minus theta, no consequence. And to change theta to minus theta, you have to change the sign in the front. And then you reverse that at the end. Okay. We want to solve x squared equal to 1 plus I root 3. I root 3 is in the first quadrant, so in polar form, the r is 2 square root 1 squared plus root 3 squared. And then the angle is 60. So that's 2 cos 60 plus I sine 60, or rather in general polar form, that's 2 cos 60 plus 360n, should really put my degree symbol in, plus I sine 60 plus 360n. There's degree symbol in there that I didn't write. So that means x would equal the square root of 2, and then that gets power a half, and so these get multiplied by a half by De Morpham's theorem. So that's cos 30 degrees plus 180 degrees n plus I sine 30 plus 180 degrees n. So we just need to put in 0 and 1 to get the two roots here. So root 2 cos 30, so that's root 6 over 2 plus root 2 over 2i, and then the second one here, cos 30 plus 180. So, oh yeah, it should be the negative, minus root 6 over 2, and then it should be minus root 2 over 2i. Okay, so that's the two solutions there for that. That's a proof there, and that's done there. Okay, next now. Looks like another transformation question. Right. So we've got the plot here. X equals 1. So this is where our k will be, just the line x equals 1. Okay. Now express u and v in terms of x and y. Great. Okay, so w, which is u plus iv, is equal to 3z, which is x plus iy plus 7i. So that means u will equal 3x and v will equal 3y plus 7. And then we want to transform this k. Doesn't look too bad. We would make this 3 times bigger and then add 7i to it. I'm not sure actually if the graph would change that much. So for example, if you have if you have x plus iy here and then u plus iv, so we'll just take the point 1 plus 0i, u would be 3x, so that would be 3, so it gets pushed out to 3, and then the y would be 3 times 0, okay, so just plus 7i, and then let's take the point here 1 plus 1i, so that would be 3, and then the v would be 10i. So I kind of, if I can delete that, or I'll just, I need to make 2 diagrams, okay. Yeah, I'll delete that. Okay, and we'll put it here. The transformation going that way. So let's just say that's 10, and then that's 10i there. So it's going to be 3 plus 7i, and then 3 plus 10i. And this here is at 3. Yeah, so well, I had to change the scale, but this gets pushed out. So I mapped these 2 points here to here. So it doesn't really look like it's changed much. Just this vertical line just gets moved out. So I think that's all finished. Strange, it's just a vertical line k. So transforming it's only, all it did was just slide it. Because the plus 7i, it's not going to change a vertical line if you move it up or down. So it's only the multiplication by 3 that pushes it out, factor of 3 from the origin, that matters here. So, okay.